All right, polyprotic acids now. What about ones that have multiple protons? For example, phosphoric acid has got 3 protons that are ionizable. We saw that we have 3 reactions of dissociation. As this happens, this would correspond with pKa1 or Ka1 more specifically. We would have the same, or rather a process can happen again, and then a third time. 2 minus there, not 3. H, nope, just phosphate. Fun stuff. So we would have 3 Kas and 3 pKas, therefore. If we look at this, we get a giant mess of a curve, but we can do it. If we again say we have 50 mLs of 0.1 molar of our acid, this time we're going to need 3 equivalence points, because we're going to have one where we equivalence, the first equivalent will get rid of that first proton, take care of that first reaction. The second one will take care of the second proton, and then the third equivalence will take care of the last proton. And so what we're going to see here is that the pKa's of these, pKa for phosphoric acid, the second one's about 7.2, so I'm going to just base this off of that. But we're going to see the following kind of behavior. We're going to see that we will end up kind of sharpening up around our first equivalence point. We'll have a, hopefully, let's try and make this, a little bit better here. And then one more. So the point is we have 3 equivalence points. We have 3 equivalence points on this graph. Calculating the pH at these is tedious and awful, and I do not recommend you do it. But you're welcome to. Have fun. It's simply a matter of using ice tables. Again, you need to worry about them because you now have more than one thing in solution. It's a mess. It's tough. But you can. But we also see at these kind of half equivalence points, halfway between each equivalence point is a half equivalence point, right? And just like before, your pKa will equal your pH at the half equivalence points. So I'll write those out. So your half equivalence points, after you've added the first equivalent, then you'll add another half equivalence, you'll find your second pKa, and then at your third one, you'll have your third pKa, at your third half equivalent. So after your second full equivalent, do half of another one, and you'll end up at pKa3. A third equivalent will get you to the third equivalence point. Giant mess that these happen to be. Usefulness? Maybe there's some, but these are not standard. We don't typically do titrations with these because of how complicated things can get. However, you can use these to kind of estimate the values of the pKa's, right? By looking at the graph, you can say, okay, well, at 25 mLs added, at 75 mLs and 125 mLs, we have our half equivalence points. And so we'll at least have the pKa's. We can reference those to figure out what our acid happens to be. That's one thing you can do. So you can determine the identity of an unknown polyprotic acid if you know, if you have like a chart of pKa's for a bunch of polyprotic acids. That's kind of the one thing I can imagine you doing with this. Typically, it's not terribly useful. As you see, there's many different things happening in this, and calculations are kind of not so useful. So I just wanted to also include that, just so if you ever see these in the future, that you have some kind of basic background about them. So Really, the takeaway here is they would have multiple equivalence points, multiple half equivalence points. Where those end up entirely depends on the acid. Phosphoric acid is one of our stronger weak acids, so it still has a fairly low pH to start, but something like citric acid might have a higher one, or carbonic acid, and so hard to say. Much, much more complicated. Thankfully, it's not something we're really going to focus on here. So we'll have that. Finally, one thing to think about when doing titrations, you can use a pH meter, which is a device that measures the voltage of a hydrogen ion within the solution and can tell you the pH as you're doing things in real time. But we also have compounds called indicators. And I'll put up a link in Discord for a kind of table of various indicators. And you'll see that some have better uses than others for certain acids and bases. There's going to be, for every indicator, a pH at which there's a color change. For example, with a sodium hydroxide HCl titration, very often we use what's called phenolphthalein. It's an indicator that turns it's clear in acidic solution, but as soon as we hit around pH 8 or so, it turns bright pink. Like, it's an incredibly obvious color change. And since we know strong acid and strong base, really, as soon as we hit pH 8, we're already just past our equivalence point. So that's a very useful indicator there. But if we're doing weak acid, weak base, we might have to think about which indicator to use, because we want that pH to be where the color change is happening to be near the equivalence point. Need this pH to be near the equivalence point. So for strong acid, strong base, you can use almost any, because the pH changes so drastically. But if you have a weak acid, you probably want to use something like methyl orange or methyl red. And these have pH changes around higher pHs. And so we'll see that there are various other ones, like for weak bases. I'm sorry, this would be for weak bases. You'll want to use the methyl orange or red. Those are for weak bases, if I remember correctly. There are dozens of indicators, by the way. Something like a weak acid, you'll use bromocresol green. Bromocresol green or blue. They have all these various weird names. But they're good for their own, uses. So these are just a qualitative way of us evaluating, okay, well, we've seen this color change, so we're at the equivalence point. Now we know to stop our titration, so we can figure out whatever we need to figure out with them. And so that's kind of just the last little bit of titrations that we want to worry about, is selecting an indicator. And for that, you just want your indicator's pH color change to be around your pH of your equivalence point. And so for weak acids that we're titrating, those are going to be slightly higher than 7 pHs. And for weak bases, if we're titrating those with strong acids, the other side of things, those will have just the opposite. All of the things we've talked about in these last couple of videos are just the opposite for bases as they would be for acids. So if you are doing a weak base strong acid titration, you start fairly high, you get a little low, and then you go crazy at the end and level out. It's just flip the graph over, and that's what they look like. So that's our last kind of section here of titrations. In the next video, we'll actually look at something beyond acid and base, which will be a solubility equilibria. And then we will come back to acid and base right after that. So don't go too far.